Dear learners, I welcome you all to the MOOC on Principles of Electrical Sciences. I am Dr. Sanjay Agrawal, Associate Professor in Electrical Engineering, School of Engineering and Technology, IGNOU, New Delhi. So, in previous session we discussed efficiency of transformer, condition for maximum efficiency and what would be load current at maximum efficiency. We have also derived expression for KVA applied at maximum efficiency. Dear learner, in this session we would discuss voltage regulation of transformer and construction and working of auto transformer, and we will also discuss what is the advantage, disadvantage and what are the applications of auto transformer. So first of all, I am going to discuss voltage regulation. Under no load conditions, the voltage at secondary terminal is E2. So you can write E2 is equal to what? It can be written as E2 equal to V1 multiplied by N2 upon N1, where N2 upon N1 is what? It is a K, or you can say it is a transformation ratio. So this approximation neglects a drop R1 and XL1 due to small no load current. So as you know, as load is applied to the transformer, the load current or the secondary current increases. So the primary current I1 also increases, and due to this current there is a voltage drop in the primary and secondary resistances and leakage reactances, and as a consequence the voltage across the output terminals or the load terminals changes. In quantitative terms, these changes in the terminal voltage is called voltage regulation. So at a constant supply voltage, the change in secondary terminal voltage from no load to full load with respect to no load voltage is called voltage regulation of transformer. Just to assume, let E2 is equal to secondary terminal voltage at no load and V2 is secondary terminal voltage at full load. Then you can write the voltage regulation in percentage terms. So you can write percentage voltage regulation is equal to what? E2 minus V2 upon E2 into 100. You can note that E2 and B2 are the magnitudes, not the phasor or complex quantities. Also note that voltage regulation depends not only in the load current but also on its power factor. Using the approximate equivalent circuit referred to primary side or secondary side, we can obtain the voltage regulation. Consider the lagging power factor load, or you can say RL load. So when transformer is loaded, there are voltage drop across resistance and the inductance. Hence no load voltage E2 is given by E2 equal to B2 plus I2 RE2E plus I2 X2E, where this B2 is a secondary terminal voltage, E2 is the induced EMF at the secondary side, and R2 is the resistance referred to the secondary side, and X2 is the reactance referred to the secondary side. So for lagging power factor load, I2 lags by the voltage B2, that is a terminal voltage, by phase angle you can say that is a phi 2, and when you are going to draw the phasor diagram, take the B2 as a reference. The drop I2 into R2E is in the direction of the I2, while I2 multiplied by X2E is at 90 degree of I2 into R2E. So here you can see in the phasor diagram what is the value of this OA. OA is nothing but it is a terminal voltage, that is a V2. Now here you can notice that if you want to calculate the value of this AF, so AF is what? AF is a horizontal component and value of this can be written as AB cos phi 2. And what is a AB? AB is nothing but it is a product of I2 into R2E. So AF is equal to AB cos phi 2 plus I2 R2E cos phi 2. Similarly, here you can see again in this phasor diagram, so you can find out the value of FB is equal to DE basically and is equal to AB sin phi 2, and it can be written as I2 R2E sin phi 2. Similarly, you can also notice that BE is equal to FD is equal to BC sin phi 2. And what is the value of this BC? Value of this BC is equal to I2 X2E. So value of B is equal to what? I2 X2E sin phi 2. Similarly, you can also find out the value of this CE. So CE is equal to what? BC cos phi 2, and value of BC is what? I2 into X2E. So you can write CE is equal to I2 X2E cos phi 2. From this diagram you can also notice that what is the value of this OD. So you can see here in the diagram, so OD is equal to what? This OA plus AF plus FD. Now just you put the value of all the component like OA, AF and FD. So OD can be written as OD is equal to V2, because value of OA is what? That is a V2. And what is the value of AF? Value of AF is I2 R2E cos phi 2. And what is the value of this FD? The value of FD is I2 X2E sin phi 2. You can also notice on the vertical component, you can see that CD can be written as CE minus DE. And what is the value of this CE? Value of CE is equal to I2 R2E cos phi 2, and value of DE is equal to I2 X2 sin phi 2. So the value of this CD, you can say it can be nearly equal to 0. Why? The value that you can see, that is alpha, which is the angle between OA and this OC, is very small. So this value can be written near about equal to 0. You can also notice that if you apply the Pythagoras theorem in this particular triangle ODC, so you can write OC square is equal to OD square plus CD square. And because this value is very nearly equal to, so this OC square can also be written as OD square. So if you put the value of this OC, so value of OC is what? Value of OC is E2. So this can be written as E2 is equal to B2 plus I2 R2E cos phi 2 plus I2 X2E sin phi 2. So approximate voltage drop is what? If you are looking at the secondary side, so drop is what? You can write approximate voltage drop is equal to E2 minus B2, and it can be written as I2 R2E cos phi 2 plus I2 X2E sin phi 2. So this phi 2 can also be written as phi. So as you know, the voltage regulation is equal to what? E2 minus V2 upon V2. So just put the value as we have already calculated. So E2 minus B2 can be written as I2 R2E cos phi plus minus I2 X2E sin phi upon B2. Or you can write E2 minus B2 upon B2 multiplied by 100 is equal to what? I2 RE2 upon B2 into 100 into cos phi plus I2 XE2 upon B2 into 100 into sin phi. So you can see the left hand side, that is equal to what? This E2 minus B2 into 100 upon V2 is equal to what? That this is a percentage voltage regulation. And on the right hand side, the first part is equal to what? Basically it is a percentage resistive drop multiplied by cos phi, and second term of the right hand side can be written as percentage reactive drop into sin phi. So here for the any transformer, the ideally voltage regulation should be 0. So as load current increases, the voltage drop tends to increase and V2 drops more and more. So you can notice here, for the lagging power factor, V2 is less than E2, and you can say it is a positive regulation. And for the leading power factor, this E2 is less than V2, or you can say it is a negative regulation. The voltage drop should be as small as possible, hence less the regulation, better is the performance of the transformer. Now we have to find out the condition for the zero voltage regulation. So as you know, the voltage regulation can be written as E2 minus V2 upon V2, and this can also be written as I2 R2E cos phi plus I2 X2E sin phi upon V2. So for the zero voltage regulation, what you will do, just you put 0 as a voltage regulation. So you can write 0 is equal to what? I2 R2E cos phi plus I2 X2E sin phi upon V2. So after the solving you can write I2 R2E cos phi plus I2 X2E sin phi is equal to what? Is equal to 0. So again after the rearranging you can write I2 R2E cos phi is equal to what? Is equal to minus I2 X2E sin phi. So this I2 from the left hand side and right hand side will be cancelled out. So you can write R2E cos phi is equal to minus X2E sin phi. So this sin phi upon cos phi is what? It is a tan phi. So you can write tan phi is equal to minus R2E upon X2E. So condition for the zero voltage regulation is what? Tan phi is equal to minus R2E upon X2E. Similarly, you can find out the phase angle phi. So phi is equal to what? Minus tan inverse R2E upon X2E. Now I am going to discuss the another type of transformer, that is a auto transformer. The transformer we have considered so far are two winding transformer in which the electrical circuit connected to primary is electrically isolated from that connected to the secondary. An auto transformer does not provide such isolation but has economy of cost combined with increased efficiency. An auto transformer is a special type of transformer in which a part of the winding is common to both primary and secondary. Auto transformer has only one winding bound on laminated magnetic core, and with the help of the auto transformer the voltage can be stepped up or stepped down to any desired value. The principle of operation of auto transformer is the same as that of two winding transformer. For step up transformer, BC acts as a primary while AB acts as a secondary. Here you can see in the circuit diagram. For a step down transformer, this AC acts as a primary while BC acts as a secondary winding. And with the help of jockey B, the number of turns can be increased or decreased, hence the secondary voltage can be adjusted as per the requirement. If you neglecting all the losses, so leakage reactance and the magnetizing current, the transformation ratio can be written as K is equal to what? V2 upon V1 is equal to I1 upon I2 is equal to N2 upon N1. So here in the circuit diagram you can notice that at the coil AB the applied voltage is what? V1, and number of turn in the binding AB you can say it is a N1, and number of turn in the binding BC is equal to N2. So here you can notice that I1 is current is flowing from the primary side which is flowing through AC, and I2 current is flowing through this CB, and the current that is flowing between B and C, that is a I2 minus I1, and B2 is the voltage which is across the load applied in the transformer. When AC voltage B1 is applied to binding AB, an exciting current starts flowing through the full binding AB. If the internal impedance drop is neglected, then voltage per turn in the binding AB is equal to V1 upon N1, and therefore the voltage across BC is what? It can be written as B1 upon N1 multiplied by N2. So as you know, in case of transformer the input power is equal to the output power. So in this auto transformer, what is the input power? Input power is V1 I1 cos phi 1, and what is the output power? Output power is V2 I2 cos phi 2. So if internal impedances drop and losses are neglected, then what is the value of cos phi 1? It is equal to cos phi 2, right? So you can write the expression V1 I1 is equal to what? B2 up into I2, and after the rearranging you can again write B2 upon B1 is equal to I1 upon I2 is equal to K, where K is what? K is a transformation ratio. Here K is less than unity. the expression is identical to a two-winding transformer, you can notice here. Let at any instant the exciting current flows from A to B and it establishes a working MMF directly vertically upward in the core. When switch S is closed, the current in winding BC must flow from B to C in order to create an MMF opposing the exciting or working MMF as per Lenz's law. Since the working MMF in transformer remains constant at its no load value, the primary must draw additional current I1 from the source in order to neutralize the effect of current IBC. In binding AB, I1 flows from A to B, while in binding BC, I2 flows from B to C. Therefore, the current in the winding BC is I1 from C to B and I2 from B to C. Hence, the current I2 is greater than I1 because B2 is less than B1, and their MMF are opposing each other at every instant. Therefore, you can write IBC is equal to what? I2 minus I1. Now, MMF of binding AC can be written as I1 multiplied by N1 minus N2, where N1 and N2 are the number of turns at the primary side and secondary side. So, this can also be written as number of MMF in AC is equal to I1 N1 minus I1 N2, and this can also be written as I2 N2 minus I1 N2 is equal to I2 minus I1 multiplied by N2, because I1 N1 is equal to what? I2 N2. So, this can be written as IBC N2, and this IBC N2 is what? It is a MMF of winding CB. It is therefore seen that transformer action takes place between the binding section AC and binding section BC. In other words, the volt ampere across binding AC are transferred by transformer action to the load connected across the binding BC. So, power transformed in VA can be written as VAC multiplied by IAC, and value of this VAC is what? It is V1 minus V2, and this IAC is what? It is a I1. So, total power to be transferred or input power in VA is equal to what? V1 into I1. So, power transformed in VA is equal to what? VAC into IAC is equal to V1 minus V2 into I1. So, total power to be transformed or input power in VA can be written as V1 into I1. So, you can also write the ratio of transferred power in VA to the input power in VA is equal to what? V1 minus V2 into I1 upon V1 I1. So, this can be written as 1 minus V2 upon V1, and this V2 upon V1 is what? It is basically K. So, ratio of transferred power in VA to the input power in VA can be written as equal to 1 minus K. So, power transformed is equal to what? 1 minus K times power input. Out of the input volt ampere V1 I1, only VAC IAC is equal to V1 minus V2 into I1 is transformed to the output by transformer action. The remaining power in volt ampere required for the output are conducted directly to the secondary from the primary due to electrical connection. So, you can also write power conducted in VA is equal to total power input in VA minus transformed power in VA, and this can be written as V1 I1 minus V1 minus V2 into I1 is equal to what? V2 I1. So, power conducted in VA to the power input in VA can be written as V2 into I1 upon V1 into I1, which is equal to K. So, power conducted is equal to K times power input. So, we get two formulas. The ratio of transformed power to the input power is equal to 1 minus K, and ratio of conducted power to the input power is equal to K. So, ratio of transformed power upon input power is equal to 1 minus K. Now, put the value of K. So, K is equal to what? V2 minus V1. This can be written as B1 minus B2 upon B1. So you can also write the inductively transformed power to the total power is equal to high voltage minus low voltage upon high voltage. Now we are going to discuss the copper saving in the auto transformer. So due to the use of single binding compared to the normal two binding transformer for the same capacity and voltage ratio, there is saving in the copper in auto transformer. Due to the single binding used, there is a copper saving in auto transformer. As you know, the cross section of binding is directly proportional to the current, and total length of the binding is directly proportional to the number of turns. So you can write weight of the copper is directly proportional to the number of turns multiplied by the current. So in a two binding transformer, weight of the copper of the binding 1 is directly proportional to N1I1, and weight of the copper of the binding 2 is directly proportional to N2 into I2. So total weight of the copper in case of two binding transformer is proportional to N1I1 plus N2I2. In case of step down auto transformer, the weight of the copper in section AB is proportional to N1 minus N2 into I1, and weight of the copper of section BC is directly proportional to N2 multiplied by I2 minus I1. So total weight of the copper in case of auto transformer is directly proportional to N1 minus N2 into I1 plus N2 multiplied by I2 minus I1. So ratio of weight of the copper in auto transformer to the weight of the copper in two binding transformer can be written as N1 minus N2 into I1 plus N2 I2 minus I1 upon N1 I1 plus N2 I2. So after the solving, you can write the weight of the copper auto transformer to the weight of the copper in two binding transformer is equal to 1 minus K. So after the solving, we get the two general expression, that is saving in the copper is equal to K times the weight of the copper in two binding transformer in case of step down transformer, and saving of the copper is equal to 1 upon K times the weight of the copper in two binding transformer if it is a step up transformer. Now we have to understand what are the advantages and limitations of the auto transformer. First is copper required is very less. Second, efficiency is higher compared to the two binding transformer. Third, the size and hence cost is less compared to the two binding transformer. The copper losses are also very less. The another advantage of the auto transformer is what? The voltage regulation is superior than two binding transformer due to less resistance and leakage reactance. So every device having some advantage, at the same time it have limitations also. So limitations of the auto transformer are as follows. First is no electrical separation between primary and secondary binding, which is risky in case of high voltage level. Second limitation is if a section of binding common to primary and secondary is opened, full primary voltage appears across the secondary, which is very dangerous. Now we have to understand what are the applications of this auto transformer. So applications of auto transformer are as follows. First, for starting rotating machine like induction motor, synchronous motor, auto transformer are used. Second application, for interconnected system which are operating roughly at same voltage, auto transformer are used. Auto transformer can also be used as a furnace transformer for getting required supply voltage, and auto transformer can also be used as a variac to vary the voltage to the load smoothly from 0 to the rated value used for dimming the light in cinema halls. Now we have to understand what are the effect of power factor on efficiency. The efficiency of transformer is given by formula efficiency is equal to output upon input, and it can also be written as 1 minus losses upon input. So as you know, input is what? Input is equal to output plus losses. So you can write V2 I2 cos phi 2 plus losses. So from the equation 1 you can also write the formula of the efficiency is equal to 1 minus losses upon B2I2 cos phi 2 plus losses. So efficiency can also be written as 1 minus losses upon B2I2 upon cos phi plus losses upon B2I2. So just you assume that losses upon B2I2 is equal to A. So this efficiency can also be written as efficiency is equal to 1 minus A upon A plus cos phi, and this can also be written as 1 minus A upon cos phi upon 1 plus A upon cos phi. So here you can notice if power factor is more than A upon cos phi is less, hence the second term in equation A is less and efficiency will be more. So as power factor increases, efficiency also increases. So in today's session, we discussed voltage regulation of the transformer and construction and working of auto transformer. Dear learner, hope you were able to learn the concept. In the next session, we would discuss three-phase transformer, its advantages, disadvantages and applications. We would also discuss connection of the three-phase transformer. All day efficiency and classification of the transformer would also be discussed in next session. Thank you very much.